So before we look at the final example in this section on radian measures, I just wanted to remind us about all of the stuff that we looked at in year 12 on the symmetry of all these trig functions and all these related solutions. So we actually had two ways of looking at this. One way was the cast diagram, and the other way was the graphs. And I'm going to start with cast, and then we'll just remind ourselves how that all relates to the graphs as well in a second. And the way the cast diagram worked was we could have an angle, and it was measured always clockwise from the x direction, and cosine of that angle was the horizontal distance, and sine of that angle was the vertical distance, and tan of the angle was the gradient. So in this little kind of right angle triangle, we actually had all three of our trig functions, cos theta, sine theta, and the gradient tan theta. And what that means is that if I take this same angle here, but I draw it over here instead, then what I get is the exact same size for cos theta, but now it's negative, the exact same sine theta, and the same gradient, but now it's negative. And if I draw the line down here, with this being our angle theta, again, cos is the same but negative, sine is now the same size but negative, and the gradient is now exactly the same as it was before. And if I draw my angle down here instead, cos is the same as it was before, sine is now negative, and the gradient is now negative. So actually, if I know the exact value for one angle of theta, there are three others that have the same size, but depending on which function we're looking at, sine, cos, or tan, the answer may be positive or negative. And the cast diagram is telling us what's going on. In the A section, they're all positive. In the S section, sine is positive, the green line, but the other two have flipped to negative. In the T section, tan is exactly the same, so it's positive, the blue gradient, but red cos and green sine are now negative. And in this section, cos is positive, the red line, but both tan and sine are negative. So in each section, we know exactly which one has stayed positive and the other ones which have flipped to negative. Actually, there's even more that we can do with this information, because there's all this symmetry going on here. I can also just say, well, so if cos of theta, that's our red line over here, well, that is therefore the same as cos of, well, a full turn take away theta. Now, previously that was 360 minus theta, but now the full turn is 2 pi. Okay? So cos of theta is exactly the same as cos of 2 pi minus theta. I can also point out where my two negative ones come from. So cos of 180 minus theta, which is actually now pi minus theta. So cos of pi minus theta, we're looking at kind of this line over here. This is now negative. So that is equal to the negative of cos theta. And exactly the same way, if I look at this line down here, this is pi plus theta. So cos of pi plus theta is equal to negative cos of theta. So I can kind of formalize all of this information with a series of equality statements where they're either exactly equal, the top one, or they're negative, the other two. And I can do the same thing for tan and for sine. Now, listing all 9 of those is fairly horrific. It's they're all incredibly similar, and it's very, very easy to get yourself muddled up with which one's which. So I would not suggest for a moment you try to memorize all that information. Instead, I would just say, sort out in your head the cast diagram, or the equivalent to the cast diagram is to look at the sine, cosine, and tangent graphs. And we just looked at cos, so let's look at cos again. Let's just pick an angle theta here. Okay, so this is my theta. So what we can also say is that over here, this is 2 pi minus theta, and it's the same. And then we've got a couple of ones that have the same magnitude, but they're negative down here. And this is pi, and this is a distance of theta. So this one is pi plus theta, and this one is pi minus theta. And these have the same magnitude, but they're negative. So I can pull those same equations out from that cosine graph, and the cast diagram and the sine and tangent graphs give us all that same information for sine and tan as well. Where is it the same size, and where is it the same size but negative? There is a page in your textbook which has all of this information in full. So you can see we've got these 3 equations for cosine, and they're the same 3 that we wrote down a minute ago, but you also have them for sine and for tan. And the suggestion is that you know all of these rules, but I wouldn't suggest you try and memorize them in this form. This form down here is kind of unhelpful. This, or keeping in your head the sine, cosine, and tangent graphs, I think is far more straightforward. Some of you will prefer the cast diagram. Some of you will prefer the intuition that comes from the graphs. And it does not matter which one, as long as you stick with it and practice it until you're really efficient at using those tools to find those repeated values. There is also this section saying you need to learn the exact values of trig ratios. You already know these. These are the ones that come from the 30, 60, 90 and the 45, 45, 90 triangles. Right? So these are the ones that come from this right angle triangle and this right angle triangle. We already looked at them. The only difference here is that instead of saying 30, we're now saying pi over 6. So this is the same thing as sine 30. It's just now we're working in radians. And the key thing here is you know these angles already, and you know their exact trig values already, at least you should. But you also need to spot and recognize them in radians as well. And we talked about that already. It's not difficult to convert between angles in degrees and angles in radians, but you need to be fairly efficient at it so that you're not wasting time tapping things in a calculator when actually they're just up in your head. If I say sine 30, you should be going, that's a half, instead of reaching for your calculator. And in the same way now, if we say sine of pi over 6, you should be going, oh yeah, that's a half. No point wasting time with the calculator. There is no real reason for knowing these facts other than efficiency and time saving in the exam. Because you have a calculator, you can always type them in, but you should be trying to save as much time as possible. So the 30 seconds it takes to tap that in the calculator to confirm it is 30 seconds wasted on a tougher question which really requires a bit more time. So everywhere you can gain some time by having those things in your head is a massive benefit in the exam.